2,000 years, we humans, the same humans who have built rockets which have sent us to space, the same humans who have utilized equations which have let us understand how waves behave, have yet to produce a machine which can detect P waves from an earthquake.
Alright, so hey guys, and so in this video for the Breakthrough Junior Challenge, I'm going to talk about how we can build an early earthquake detection algorithm to warn people by using phones, Bayesian probability, electromagnetic waves, and a few other methods. So let's get started. So my name is Rifat, and today we're going to discuss four things. First, the earthquake's attributes and characteristics. Second, the first method to detecting an earthquake, the social media keyword algorithm. Third, detecting an earthquake using electromagnetic waves. And fourth, using a phone accelerometer to detect an earthquake. So let's begin with the earthquake attributes and characteristics. Alright, so hey guys, we're going to now talk about an earthquake's attributes and characteristics. So an earthquake always starts off with two types of waves. First, we have the P wave. Let's actually generalize it a little bit more. First, we have the body waves. The body waves are the waves which travel through the earth, so they arrive at their destination much quicker than the surface waves. The surface waves actually go around the earth. So let me show you that for a second. So this was the planet Earth. The surface waves would start off here from the epicenter and go all the way to the other side. So it goes around the earth, taking longer. So now let's get a little bit more specific. There are two types of body waves. We have the P waves and the S waves, and there are two types of surface waves as well, the love waves and the Rayleigh waves. So we're going to focus on the body waves a little bit more today. So we have two types of body waves. First, we have the P wave and then the S wave. So the P wave can travel through all states of matter, including solid.
Why you gotta take so long?
Alright, fine, speed it up, folks. So it can travel through solids, for example, the Earth's crust.
You're still very slow.
You still talk like Bigfoot. So, we would say that this is the Earth's crust, and that this is the Earth's mantle. So, a P wave can travel through solids, such as the Earth's crust. It can also travel through liquids, such as tsunamis. So, an earthquake can also travel through such types of matter, for example, tsunami. And that's why it is warned that when a heavy earthquake occurs, a tsunami may also travel forward with that earthquake. So P waves can travel through most types of states of matter. Now, a P wave is also slower than an S wave. That's why a P wave it's faster than an S wave, so it actually comes first to the destination. So this is the epicenter of the earthquake. The P wave would would go faster at about 2.8 meters miles per hour. While the S wave would travel at about only 2,000 miles per hour. So, if we looked at a seismogram, this is how it would appear. We would have the earthquake epicenter, and then shaking from the P wave. So we know that right over here is the start of the P wave, and once the P wave ceases, we have the S waves, which are a lot more stronger. So right over here we can see is the start of the S wave. High contrast color. So this would be the start of the S wave. Now, an S wave can only travel through solids. So, for example, if a tsunami occurs because of an earthquake, there will never be like a double warning like an earthquake. There will only be the P wave, no S wave. So an S wave can only travel through solid. Now we're going to discuss about how we can detect the epicenter of the earthquake. So now, to find the epicenter of the earthquake, we must start off with the location. So I started off with the location as New York. So let's take a look at the seismogram for the earthquake in New York, and let's find a spike in the data, a sudden movement. So let's try to find that sudden movement. So here we see a little variation, and then suddenly a huge spike in the seismogram. So we'll circle that, and we'll mark that as the beginning of the P wave. So this 20 seconds is the beginning of the P wave. So let's mark that. So to find the distance from the epicenter of the earthquake from the city, we must use this little graph over here. So let's take another piece of paper. Now let's mark the lag time. So the lag time for us is 95 seconds. This is in minutes. I believe we have found it. So now we can see that has to be really accurate. Okay, so now let me just, this isn't quite accurate really, but we'll have to deal with it. Okay, so we see right over here. Alright, so that right over here is our distance from the epicenter. So that's right about 1,700 miles, just about. Now, how do we plot that on a map? Well, before we do that, let's just finish up our data table. 1,700 miles. Okay, so we finished our graph as well as our data table, and we know all these aspects about the earthquake. We know the initial P wave arrival time, the initial S wave arrival time, the lag time, and as well as the distance from the city. Now we're just going to plot that right over here on our map, on my very crude map. So this is New York. We're gonna find
whatever distance is. So let's say this is 1700 miles. It probably isn't, but let's just say it is. So the earthquake could have originated anywhere from 1700 miles from New York City. So it could have originated here, it could have originated here, anywhere 1700 miles from the city. So it has infinite number of starting points, and that is how we find the distance, the epicenter of an earthquake.
Alright, so now that we know the attributes and characteristics of an earthquake, let's move on to how to detect an earthquake using social media. So for example, let's say we have something like Twitter. So to build an algorithm that detects whatever tweets are warning an earthquake, first we have to detect the keyword. So for example, quake, UTC for timing, minutes for also timing, ago if it's compensated with minutes, location if the location matches any of the locations in a specific array. So for example, I'll have an array that has all the locations, all the countries on Earth, and as well as the Richter scale of the earthquake. So for example, M followed by a real number with a decimal. Second, to build our algorithm, we have to get all the messages that contain those specific keywords and store them in an array. So if we make an array called all tweets, that would store all the tweets that have those specific keywords. Third of all, to get even more specific, we want to use the floor function to round the number of minutes since the tweet was posted since the earthquake. So for example, if the tweet has minutes, so for example, in this tweet it says Justin 50 earthquake 557 GMT MT. Did we just have an earthquake? So it'll measure that time minus the time the tweet was posted, and it'll find the number of minutes since the tweet was posted after the earthquake. So after that, we're gonna list the top 3 messages posted after since the shortest time after the quake, and we're going to copy the warning from those tweets across all governmental phones within the specific radius of the earthquake speed wave and so that's how we'll use a social media for like Twitter or Facebook or something as such to warn users of an earthquake. So now let's move on to how we can utilize electromagnetic waves to detect earthquakes. So let's say we know that an average earthquake, or for example a sample earthquake, emits from 0 to 20 hertz of electromagnetic waves from the epicenter. So what can we do to detect those electromagnetic waves? Well, we know that an antenna can detect those EM waves, so we can just wrap an antenna around the base of the phone and stick a part of that antenna out so that the EM waves from the earthquake can be detected. And so that's how we utilize EM waves to detect an earthquake. Now last of all, we can utilize the phone's accelerometer to detect an earthquake. So how can we do that? Well, if you take a look at the iOS developer library, we'll see something called a piece of code called the accelerometer graph. That accelerometer graph graphs out the motion that the phone is shaking, or its roll and its axis. So its pitch, its yaw, its roll, it's basically its angle of movement. So we can plot any significant shaking within the graph of the accelerometer due to the earthquake. So for example, the earthquake, even if the person who's using the phone doesn't realize it, the phone accelerometer will graph the slight shaking. That significant sudden shake will cause an alarm, a chain reaction basically, in which, so this is the first person who gets alerted of the earthquake. So when the P wave happens, his phone corresponds with the next person's phone. Now, how can we verify it really is an earthquake and not a false alarm? Well, if we can measure the distance from the P wave to the person and the distance and the combined distance from the first person to the next person, and it should be almost like a right triangle. So that person should be warned in about seconds after the first person is warned. If so, then it really is an earthquake, and we have verified an earthquake within the fraction of a second. So while his phone corresponds with both of these guys' phones, their phones correspond with his phone. So if both of them are parallel to the earthquake, then we can also verify for a second time that it really is an earthquake while we transmit to this person's phone. And finally, these two people's phones will correspond with the last person's phone, who will actually get the warning last, because since he's the farthest from the P wave from the other people's phones, he'll get the warning seconds after the first person. And so that is how we utilize a phone accelerometer to warn people about an earthquake, as well as detect one.